So far, we've developed our idea of standing waves on strings and in columns of air by talking about superposition of two waves, where the two waves were an incident wave and a reflected wave. They came together and they exhibited interference, which means they added together, and sometimes it was destructive and sometimes it was destructive. We're going to move now to what if we have two sources? What happens with the interference then? I'll start off with a quick demo here. What I've got is that same online tone generator, but I'm playing two different sounds. We're actually going to be able to hear the interference. This could be a little bit loud, so you might want to turn down your volume before we go on to the next little bit. Okay, so I guess you could hear that as I changed the frequency of one of those two online generators, the sound that we could listen to changed. That's the interference of sound from two separate sources, and we're going to start talking about what happens and how we describe that. I'm going to give you the physical setup now before I go on to draw pictures in the next slides of what I mean by two sources of sound. The picture you see on the slide shows two sources, two speakers. For my two sources, I'm going to have one little pink speaker and one cell phone. So in the pictures I'm going to draw, I'm showing that I have one source a certain distance away from my ear, and another source that's a little distance away from that. So I have two sources. As we get started, they're both going to be playing exactly the same sound, and we'll discuss what the interference is, what happens, and what sort of things we hear. In our setup now, we've got our two speakers emitting sound. Speaker 1 emits sound that comes out on a wave. Speaker 2 emits sound, which comes out as a wave. Drawing them in different colors so you see those waves on top of each other. This diagram is pretty messy where they're on top of each other. So in a separate diagram, I'm just going to separate them, draw them below each other. But in reality, they're all in a straight line. So there's our speakers. They're emitting sound. Something important is that the sound comes out what we call in phase. It means it comes out in the same way. So for example, the two speakers might emit sound both coming out on a crest or both coming out on a trough. That's what we mean by in phase. So there's a person here listening where they're all in a line. She'd be right there. Where I've got them separated, I'll draw a person right here. Okay, we're going to ask, what does that person hear? What's the interference? As a quick recap, let's remind ourselves about superposition. So the resultant wave that's happening in this space is that the two waves add up. So I'll add this bit and this bit. I get a line here. Looks kind of like this. So I add this bit to get here, a crest and a crest to get this bigger crest, equilibrium, 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 trough, trough, big trough, crest, crest, big crest. So that's what the resultant wave looks like. That's the superposition of waves 1 and 2. We see that those waves are perfectly lined up. This is a case of constructive interference, because they're adding up together everywhere. So if we ask, what does the person hear? We notice that the waves, when they meet at her ear, they meet crest to crest. So that's constructive interference. And in terms of sound, it means we get one loud sound, we play another loud sound, those two louds add up, and the result is really loud. So constructive interference for a sound wave means loud sound. There's our qualitative description. We also want a mathematical description. So let's put these sound waves and the interference in terms of some distances and the wavelength. So first I'll define a distance d1. D1 is the distance between the person and speaker 1. So from here to here is D1. The distance between the person and speaker 2, let's call that D2. And then the difference between those things, let's call that delta D. Now, we don't care what the difference is, or we don't care which one is bigger, so I'll use absolute values. It doesn't matter if D2 is bigger or D1. We just care how different they are, and we call that path difference. Now, people tend to find this idea tricky, so make sure you keep straight what D2, D1, and delta D stand for. It can get a little bit tangly. Okay, let's look at the problem we have. What is delta D in our picture? Well, delta D is D2 take away D1. So let's label that on the picture. We know that wavelength is important with sound, so how does all this correspond to the wavelength? So let's look at the sound coming out of the speaker and how much of that corresponds to delta D. Notice that delta D is equal to 1 wavelength. So in our picture, we have delta D equals 1 wavelength, and our person hears constructive interference. Okay, so now we're starting to build our mathematical description. It's important what the wavelength is, and it's important what the path difference is. Okay, let's keep our same setup, but change it just a little bit. Let's move speaker 1 to the right. Let's go through our same setup. Let's label D1 and D2. D1 is our person to speaker 1. Let's label D2, that's our person to speaker 2. And our person is listening right here. And delta D is D2, take away D1. So let's get delta D in our picture. Now let's ask, what does our person hear this time? Well, the person has a crest coming from speaker 2, a crest coming from speaker 1. So those waves are meeting up crest to crest, which means constructive interference, which means the person again hears a loud sound. All right, let's put that together with delta D and a wavelength. Let's look at the wavelength of our sound and where that fits on our picture. So I've got my first wavelength coming out of speaker 2. There's one full wavelength. I'm going to label that down below, lambda. Okay, and then I've got another wavelength. Why don't I even do that in a different color? There's another wavelength. That's right where speaker 1 lines up. So that's a second wavelength, lambda. So what we see this time is that delta D equals 2 lambda equals constructive interference or loud sound. That leads us to a general result, and I think I'll write this out because this is a good note to have. So our general result is that when two sources emit sound in phase, and remember that means the sound comes out of each speaker, say crest to crest or trough to trough, but they come out in the same point in the cycle. We get constructive interference. Whenever the path difference delta D, which is D2 minus D1, so the difference between those two distances, is some integer multiple of the wavelength. Okay, so whenever we meet this condition for two sources in sound, a person is going to hear loud sound. So now let's go again with our same set of speakers. They're emitting sound in phase in the same way, but now we've shifted speaker one to a different spot than it was in the previous pictures we've looked at. Let's ask what kind of interference acts at the dashed line. So we've got our friend listening right here. And again, if we want to review the theory, we have two waves. They're going to add together. So the superposition of those waves. So if we look at the spots, so we get a trough meets with a crest. That's going to give us a 0. And then we have a crest meets with a trough. That's going to give us a 0. And here we have an equilibrium with an equilibrium. That's going to give us a 0. And that's true everywhere. Or trough to crest, equilibrium to equilibrium, crest to trough. So our wave is 0 everywhere. So here we have complete destructive interference. So the waves cancel. So if we ask what kind of sound does the person hear, we see a crest from wave 2, a trough from wave 1. Those two waves cancel. So we have destructive interference where our person is this time. So the waves meet crest to trough. That's destructive interference. The waves cancel. In terms of sound, this is going to be quiet. If the universe were absolutely perfect, I suppose we'd say silent, but things are rarely perfect, so we'll just say quiet instead of silent. Okay, let's deal with our path difference like we did before. So our path between speaker 1 and our person is D1. Speaker 2 and our person is D2. Our path difference, delta D, is the difference between D2 and D1. We take the absolute value because we don't care which is bigger. And let's see what that turns out to be in this picture. So our waves are emitting sound in phase. So here's speaker 1. Let's just draw that line up. There's the distance between those two guys. Let's also draw that on our picture. Delta D is D2. Take away D1. So this distance in right here is delta D. And we see that when our waves meet up crest to trough, our delta D is a half of a wavelength. So if those two speakers are shifted by a half of a wavelength, we get destructive interference and quiet sound. So we get 1/2 lambda. Now we could take our speaker and move it a wavelength to the right. We could move it over here and we would still get that crest to trough interference and we would still get destructive interference. So our general result, so it would be also true if delta D was 3/2 lambda or 5/2 lambda or so on. So our general conclusion then, or our general result, is that destructive interference happens whenever the path difference is off by a multiple of a half a wavelength, an odd multiple of a half wavelength. So destructive interference occurs for sources in phase whenever our path difference delta D equals the difference between D2 and D1, take the absolute value because it doesn't matter which is bigger, equals n times lambda over 2, where n is 1, 3, 5, and so on, because this means that the waves meet crest to trough. Okay, so that's how we get our destructive interference for sources that are in phase. So I've been stressing that our sources have been in phase, which leads us to the idea, well, what if they're not in phase? What if they're out of phase? And what we mean by out of phase, for example, is speaker 1 might emit on a crest, and speaker 2 is the opposite. So speaker 2 on a trough. So they emit sound in opposite ways. Then what kind of interference do we get? So I've got my same setup here. I've got speaker 1 and speaker 2. I've got my person listening. I see in my picture that the person has waves that meet up crest to crest. So I've got crest to crest. That means constructive interference, which means loud sound. Let's put this in terms of D1, D2, delta D, and lambda. So delta D is equal to D2, take away D1, equals. So what fraction of a wavelength is this? So delta D is my distance, D2 minus D1. So D2, take away D1. So here's my delta D. Let's see what fraction of a wavelength this is. So that's a half of a wavelength. Okay, so if our waves start out in different ways, we can still get constructive interference, but only if the path difference is different by a half of a wavelength or 3/2 of a wavelength or so on. So essentially what happens is for constructive interference for waves out of phase, that's the same condition as destructive for waves in phase. If you have waves that are out of phase, it's like your initial conditions have flipped, right? They used to be crest to crest and now they emit crest to trough. So it means our conditions for constructive and destructive switch. So that's a way you can remember it if you wish. So if we have two sounds that are out of phase, we get constructive interference if delta D is D2 minus D1 equals n lambda over 2, where n equals 1, 3, 5, and so on. Okay, so that's how we get constructive interference if our waves start out in out of phase. Okay, how about now destructive interference? We've got our same setup. We've got a person standing here. We've got our two speakers. We see speaker 2 ends at a crest where our person is. Speaker 1 ends at a trough, so our waves are meeting up crest to trough. That's destructive interference. Destructive interference means, oops, I almost wrote down loud, means quiet sound. Let's put this in terms of delta D and the wavelength. So delta D, our path difference, is D2, take away D1. So we're going to take D2, we're going to subtract D1. What we get for our answer is delta D. Let's see how that's related to a wavelength. So we see that that's equal to 1 full wavelength. So if they're already starting out opposite, one's on a crest and one's on a trough, anytime delta D is a multiple of the wavelength, then we will get destructive interference where our person is listening. So equals lambda. It would also be true if it was equal to 0 or 2 lambda or 3 lambda or so on. So our general result for destructive interference, if our waves start out of phase, is that delta D, which is D2 minus D1, equals n times lambda, where n is an integer, 0, 1, 2, 3, and so on. So here's a slide where I've just put it all together rather nicely. We get constructive interference if waves meet crest to crest, destructive if they meet crest to trough. If our waves start out in phase and our path difference is a multiple of the wavelength, that's constructive interference. If it's a half multiple, that's destructive. If the waves start out of phase, that means that our conditions for constructive and destructive switch. Okay, so here's your summary slide if you want a reference for your equations. So here's an application of constructive and destructive interference that I bet lots of you are familiar with, and that would be noise canceling headphones. There's a picture of me in my new gamer headphones. So when you have noise canceling headphones, the first thing you do is you put your headphones on, you hook it up to your cell phone, and you play some music. Then there's a microphone attached to the headphones that records external noise, traffic, fans, people talking, just stuff that's outside. Then the electronics inside your headphones, they convert that sound, that recorded sound, into a wave, and it plays back the wave, but it inverts it. So rather than playing it the way it came in, it plays it back upside down. So that means as it plays back that inverted wave, the external noise is canceled and you don't hear the external stuff anymore. Another example is when you're hooking up your speakers. Now this really only applies to people who have a stereo system with external speakers. You definitely wouldn't notice this if you're just playing music on your iPhone with your headphones plugged in. But if you have a set of external speakers, there's a place in the back where you plug in your speaker wires. And you'll notice that they're labeled left and right, and it matters which wire goes into which one. And that's because the sound has to come out in the same way. If you take those wires and you flip them, the sound will come out in opposite ways. So the picture we drew had sound coming out in exactly the same way. It came out and immediately went to a crest. But if one sound came out and went to a crest, and the other sound came out and went to a trough, you'd get cancellation of the sounds, and the music you played on your speakers would sound terrible. And this happens all the time. If you do a Google search for why aren't my speakers working, one of your first hits will be to check your speaker wires and make sure you connected them properly.